There's a lot we don't know about our universe, and black holes are an especially strange phenomenon. Scientists have found that black holes are a region of space having gravitational fields so intense that upon entering its event horizon, no matter or light can escape it, shredding any form of matter that enters into its most basic form of particles. Also known as the point of no return, an object requires a velocity greater than that of the speed of light in order to escape this region. This is why when we look at a black hole, we see nothing but black because no light is returning to our eye.
Naturally, nuclear fusion takes place inside the core of stars, where atoms are compressed so close together they fuse into bigger elements and release radiation. For example, two hydrogen atoms would fuse to form helium, then carbon, then other elements. The radiation released during fusion opposes the force of gravity and balances the two forces. Though after a while, this nuclear fusion continues until it forms iron through a process that doesn't release energy. This buildup of iron causes an increasing imbalance between gravity and radiation, eventually to where the gravitational force is so much greater than the opposing force that the star collapses on itself to form either a dwarf star or a black hole. In theory, any form of matter can become a black hole if it is compressed into a sphere with a small enough radius. The critical radius required for matter to turn into a black hole is called the Schwarzschild radius. If someone wanted to turn themselves into a black hole, an average person with mass 70 kilograms would need to be compressed into a size of 1 times 10 to the negative 23 centimeters cubed, a size 1/60th of a grain of sand. In other words, you would need about 1/6 people to create a black hole with a radius equivalent to that of a grain of sand.
Interestingly enough, if the sun were to be compressed into a black hole of equal mass, the force of gravity between it and the Earth would remain the same, meaning that the Earth would continue to orbit as though nothing had occurred. This is because the mass of the two objects and the distance between their centers of gravity would remain the same.
However, when more bodies of masses are sucked into a black hole, its mass, size, and gravitational pull would increase. This can be visualized by treating space and time as a single entity, called space-time, in a three-dimensional plane. We can use a form of cloth and some balls, where the cloth represents space-time, and the balls represents bodies of masses, and the dip formed in the cloth will represent the warping of space-time, in other words, the effects of gravity. And as you can see, as more and more balls are added to the center, you can see a greater dip in space-time, or, in other words, the force of gravity of each mass.
Now you might be wondering, if black holes increase in mass and size, can they ever disappear? Well, over time, black holes begin to evaporate due to Hawking radiation. While an observer may see empty space within the black hole's event horizon, black holes are actually filled with virtual particles that are pushed together and annihilate each other on impact, causing a release of energy. However, when these pairs of virtual particles appear at opposite ends of the event horizon, one particle is being pulled with a larger force of gravity than the other. So instead of colliding, they're pulled away from each other, meaning no energy is released from the particles' collision. Over a long period of time, this loss of energy accumulates, decreasing the size of the black hole until it completely evaporates and releases one final blast of energy equivalent to billions of nuclear bombs.
Another interesting fact about black holes is that you can technically use them to travel through time. This can be explained through Einstein's theory of general relativity, where if we were to treat both space and time as a single entity called spacetime, then time would pass by more slowly in a gravitational field. For example, time passes more slowly on Jupiter than it does on Earth due to its stronger gravitational pull. And if you were to spend 50 years on the surface of Jupiter, you would be approximately 31 seconds younger than if you were to stay on Earth. But in the case of a black hole, its mass and gravitational pull is so strong that time almost comes to a complete stop. So, this means that the distortion of the perception of time varies based on the force of gravity exerted on the person.
Thanks for watching, and we hope you learned something new about black holes today.